Hi guys. So hopefully I'll get this up by 4 o'clock so you guys actually take notes on this. Hee hee. Um, there's only a couple slides on here. It just has to do with finishing up the structure of the sarcomere and specifically the actin and myosin inside. So this is just kind of a continuation of the last set of notes that we did, 5-3. So this one's 5-4. And we are going to be taking a look at, oh, not 54, 5-4. We're going to be taking a look at just some of the other players that are involved in the contraction of the sarcomere. So, starting with the myosin, as you remember, the myosin is one of the filaments that are found inside of the myofibril. And what it is, it's got this long, it kind of looks like a golf club, like this. And there's actually two of them. There's another one that's kind of woven around it, like this, and goes like that. And so what they do is they line up where some point one way and then another set will point this way. So it ends up with a whole bunch of myosin here in the middle and then a whole bunch of the little golf club heads on either side. So myosin is just a rod-like tail with two globular heads. So each one has two little golf clubs on it. And the heads are where they have, like if I look up close on it, like that, they have a little divot right there, and that's where the actin goes. So the actin binds to there. And then of course we have the actin, which is, as we saw from the other diagram, it's two chains that are kind of linked together like that. But they have a couple of other proteins around it. We've got the troponin, which are these little guys. There's three of them, and they just kind of sit every so often on the actin. And so it's a 3-polypeptide complex. So when you look at it up close, you'll actually see three little structures tied together like that, and they're just found periodically along the actin. And then we have tropomyosin, which is what looks like little rods that hold it all together. So the actin, if we look very carefully up close, we see that it's actually made up of little bundles. They call it G-actin, standing for globular actin. And so these little globs, they kind of spin around each other doing this thing, kind of like that. And then there are little rods. There are little rods that go down the length of them. So that one goes like that, and that one goes like that. And so they just kind of hold everything in place. So tropomyosin is a rod-shaped protein that spirals around the actin strands and just kind of holds it all together. Then we have what's called the cross bridge, which is when the actin, so there's an actin, binds to the myosin head like that. That little structure right here is called the cross bridge. So it's just the structure that's formed from the actin and the myosin. And then don't forget we have the titin, which is the slinky that kind of holds it all together. So if we have the myosin like this, and then we have the actin around it like this, then the titin is the little springy coil that kind of holds it all together. So I've got a better picture of this for you on the next page, right there. So here's the actin, and up close we see it's made out of a whole bunch of little circular globular proteins, so G, globular actin molecules. And then we've got the ropes, these big blue ropes that kind of hold everybody in place. That is the tropomyosin right there. And then we also have the troponin, which is this guy here, here, and here, all over the place. They're all over the place on there. Remember, they were the chaperones that are causing everything to be blocked. Here's a structure of the myosin. So what I was attempting to draw, said it's two tails, and they kind of fuse together and make the two heads. And then you put a whole bunch of them together like this, and the heads pop off in various locations all around, and that's what binds to the actin in order to make the two attach. They each have a spot, so he's got a little spot there that allows him to attach here. He even has a little spot here that allows him to attach there, so they're kind of made for each other. And then down here is just showing the titin. So we have actin here, myosin here, titin here, You can see the coils, the little springs that kind of extend out and then will bring the myosin back to place when it relaxes. Okay, now also inside of the cell, so here's a cell, a fiber, and it's got lots of the little myofibrils in there. And so this is one myofibril, okay, just one pencil lead. And they are completely covered by this blue stuff right here, which is called the SR, or the sarcoplasmic reticulum. So here's the word right here. Sarcoplasmic reticulum, which is the same as the endoplasmic reticulum, just a little bit more fancy. It surrounds each and every myofibril completely, and his main job is to regulate calcium levels to go in and out. So calcium goes in and out of the SR. Also surrounding each myofibril, we have what's called a, whoops, my T disappeared, the T tubules, which are these guys right here. And they're just part of the sarcolemma, where they kind of dip in like that, but it doesn't really show it that well on that picture. And so the T tubules, they run parallel. No, they don't. They run perpendicular. Sorry about that. The T tubules right here. The T tubule, let me erase that and start over. Okay, so the T tubule right there is this little guy. Right there and right there. So if this is the length of the myofibril, they're actually parallel to it. Sorry about that. I said parallel, didn't I? Perpendicular to it. Okay, you can see it right here because apparently I can't talk. So it's perpendicular to the length of the myofibril. And then we have what are called terminal, which means end, cisternae, which means like pocket or container. And so they are these little bags of SR on either side of the T tubule. You can see it right there, terminal cisternae. And so what they do is they just kind of grab onto and hang on to calcium ions as well. And then together, if I highlight the two cisternae and the T tubule, so there's 1, 2, 3 structures, they call that a triad. So a triad is just the T tubules and the two cisternae on either side. So let's try this one more time. So all the blue, this is all SR, sarcoplasmic reticulum, completely surrounding a myofibril. And then the SR kind of pooches a little bit bigger right here to make the terminal cisternae. And then we have the T tubule, which kind of is perpendicular to the myofibril and helps to deliver materials. And then the three together right here make up a triad, like that. Now the T tubules are also adjacent to, if you look underneath, it's kind of hard to see, but it's where the A and I band match up. That's where you can always find the T tubules. Okay. Oh, there it is again. So T tubules is just a portion of the SR that penetrates the sarcomere. So remember, the sarcomere is the unit between the Z lines. You know, all that stuff, that's the sarcomere. So the T tubule, you can see it kind of goes and dips in like that. And it goes into and actually penetrates into the sarcomere there. And we can always find it between the I and the A band. So the I band, the light band, the A band, the dark band. And then once again, we mentioned this on the previous page, but we have the triad, which is the T tubule and two adjacent terminal cisternae. Okay, so let's see, I think that's all that stuff on there. So the last little bit then is what we're going to get into, which is called the sliding filament model of contraction. That's what the guy was talking about today, that those scientists, Huxley, that they're the ones who came up with this in 1954. So they came up with the fact that muscles only do two things. They contract and they relax. The contraction is when we activate the myosin's cross bridges. So that's when we take the actin and we hook it up to the myosin. Relaxation is when they let go and then everybody goes back to their normal size. So the cross bridges become inactive and the tension in it declines. So this led them to come up with what they refer to as the sliding filament theory. And all that says is during contraction, the thin filaments slide past the thick ones, so the actin and myosin overlap. So we have the actin like this, we have the myosin in the middle. And so if this is rested, then in a contracted one, the myosin stays the same length, but what happens is that the actin will overlap and shorten. So if like here's the Z disc here, well now the Z disc is like right there, and so it shortens it up. So some typical things that we see is that the Z discs will get closer together, the I band, the light band, will shorten, the H zone, that middle area, will disappear, and the A bands will get closer together. So I have a picture for you of an actual muscle right here. So you can see on this one right here, there's a Z line, there's an A band. The I band would be here, that would be the I band. There's the H in the middle with the M line, so the H is here to here. There's the M line, the little guys in the middle. And so here's a diagram of this one right there. So here's the M line, here's the H zone, here's the dark or A band, here's the light, whoops, to there, there's a light or the I, there's my Z disc right here. So if I look at a resting one, it looks like what we've been learning. If I look at a contracted one, we notice that the actin moves inwards, we can see there. But notice that the length of the A band stays exactly the same. It's only that the Z lines get pulled closer together. So the H zone gets smaller. I'm sorry, I said the H was here. Remember, it's between the actins. So that's the H zone. So the H zone gets smaller. So it goes from here to here to here to here. So there's the H zone. The Z's get closer together than they were previously. The H stays exactly the same. What else? There was some, oh, the I bands get smaller. So the I band, which is from here to here, is now here to here. And so it gets smaller too. So looking at these two pictures, we can see the difference, especially right here in the I band, how much shorter it is. And then the H zone, which is from here to here, is now here to here. So it's a little bit smaller too. Okay, so that's it. So the next thing we're going to learn is the actual chemistry behind the calcium, starting with the brain, sending an impulse down to the muscles, and then the whole calcium exchange and the troponin getting out of the way and all that fun stuff. So I just wanted you to have a little bit more background on all the bits and pieces first. Okay, so let's see, it's 3:40. I got 20 minutes to download it, and you'll be able to watch it. All right, bye.